Welcome to Breadboarding. In the previous video in the Programmable Logic Devices series, we looked at the ATF750C complex programmable logic device, so this is a bit more sophisticated, and we also covered the fact that we needed to use a slightly more expensive programmer to program these. So this is the XGECU T56 which I have, which is capable of programming these chips. Now, I had an email from Peter, so thanks for the information, about using the ATF1504 series chips. Now, these are surface mount chips. However, in the recent Breadboard PC series, I've actually been using a surface mount chip for a serial controller, for a UART, soldering the very, very small chip onto one of these sort of dip type converters. This is an Adafruit surface mount to dip adapter, so when we solder a chip onto these areas here, then we should then be able to use on the breadboard. And the 100-pin one is going to be a bit more of a challenge, but I have got some of these adapters here, so we'll look at how to use these. And I've also purchased a cheap and cheerful programmer, so this is apparently one of the Atmel ones, but it's just without the case. It was available on eBay for about £25. So this is part 7 of the Programmable Logic Device or Complex Programmable Logic Device series, and we're going to be looking at the ATF1504 44-pin surface mount and 100-pin surface mount chips. So first of all, thanks to Peter for emailing me advice about this stuff. So I have actually ordered a couple of these chips, which have now arrived, and also the surface mount dip adapters. I've also now got the Atmel USB programmer. However, it is out of stock at a number of suppliers. And the main thing that's different between this and other chips is that you don't actually plug this into a EPROM programmer like the other chips. This actually uses in-circuit programming via a JTAG cable. So this is what the original Atmel USB cable and programmer looks like with the JTAG cable here. And you can see that this is very similar, it just doesn't have the case. The LED pokes out through there, but I have tested this with the software from Atmel and it does appear to work. So let's take a look at the chips themselves. So they're in this packaging which has a lot of moisture prevention. The 44-pin ones got a fairly wide pin spacing, I think 0.8 pin spacing, so those are not too bad. The 100-pin ones are a little bit bigger, but you can also see that they have 0.5mm pin spacing, so those are going to be a little bit more challenging to deal with. So I'm going to look at the 44-pin one first, and then we'll have a look at the 100-pin ones after that. So I have got a microscope, a digital microscope that I used in the Breadboard PC series when looking at the serial surface mount chips, serial controller surface mount chips. So I'm going to solder one of these chips onto one of these. Break the end connector off. Okay, so the main thing about soldering the sort of surface mount chips is we need a lot of flux, and we probably need to tin these connectors first. And I'll be looking at this under the microscope for most of this. So when we come back, hopefully we will have soldered the surface mount chip on there, and we'll put all of the pins on there. So I've got pins here to solder onto this dip adapter. Okay, so hopefully you can just about make out what models these are. These are ATF1504 AS NAU44, so that means these are 10 nanosecond devices. There is a 7 nanosecond device, but we don't really need it quite as fast as that. I'll just try picking one of these up and see how well this matches up with the dip adapter. So pin 1 is at the top there. And the challenge always with these is to actually get the pins lined up and to tag it into place before we actually start soldering it. So I'm going to put that under the microscope, and I'm just going to tin the contacts, tag it on, and then hopefully we'll come back once I've then connected all of the dip pins also on the connector. Okay, so just going to put some flux on the various pads there, a little bit of solder on the tip of the soldering iron, then brush it across a couple of times. and that should actually tin the pads there. Okay, so I've washed the water-soluble flux off there, and we'll just have a look under the microscope to check everything. That looks like all of the solder is on those pads quite nicely. So now I'm going to put the chip on there and see if we can now actually solder the chip on. So just going to try and place the chip at the top. This was a bit fiddly. I managed to get it tagged on with some solder initially. It wasn't quite lined up on one row of pins, but it was good enough. I'm just going to touch it with the soldering iron there. It wasn't quite lined up properly. Then I was able to get the other sides to be soldered, so you can see with sufficient flux solder, if we get bridges there, then we use the braid to tidy up the solder bridges. More flux, and then that just tidies it up. Then the next one, bit of braid to clean it up. A little bit more flux, and that tidies it up. And the next side, that one on the end wasn't quite done properly. And this one, that you can see they weren't quite lining up quite, probably about a quarter of a millimetre or something like that out, but it was okay. There weren't any shorts there, so that was okay. So just clean that, and we're just checking each of the joints and things just to make sure there are no ridges or dry joints. That all looks okay. Now we're going to put the pins into the dip socket, so just put some flux on each of the pins there and just alternate the sides so we don't melt the plastic on the breadboard there. It's an old breadboard I tend to use for doing this. You can also see the 100 pin adapter on the left hand side there. Just look at the pins under the microscope just to check they're all okay. And those all appear to be pretty good. I'm also going to just test with a continuity tester. I'm basically testing each of the pins on the breadboard against the pins on the chip with a continuity tester, and that all works out okay. Okay, so now that we've built our dip adapter for our surface mount chip, how are we going to program it? Well, I've already talked about the USB programming cable, and the way how Atmel and Microchip originally designed this is that there is a development programmer kit available, which is about $265, which includes the USB cable and includes a couple of 44-pin chips as well. Unfortunately, that's out of stock, certainly at the moment, and not likely to get back in stock until May or June, according to the website. But if we have a look at what's included, this is the user guide for the programmer kit, and you can see that you get the programmer board, you get some adapters, you get the download cable, the USB download cable, and two Atmel 44-pin TQFP sample devices. So those are the ones which we're using. If you look at the board here, it's kind of like a project board that allows you to test things, but also has sockets here to plug in various adapters so you can actually program the various chips. However, in order to actually program the chips, all we really need is a handful of connections wired up to various pins and the JTAG connector connected. So let's take a look at what we need for the JTAG connector. So it's the 10-pin header pinout, and this diagram comes from that document. And you can see that out of the 10 pins, 3 are not connected, 2 are to ground. Now I found the VCC on my cable wasn't actually connected, so there's no 5 volts coming out on that, so I'm not using that. And these 4 pins here are the JTAG pins. Now the documentation in various places does mention that you might need to include pull-up resistors on the TMS and the TDI, and certainly when I didn't include those, then the programmer wouldn't detect the device properly. So I've included 2 10k pull-up resistors to 5 volts, the TMS and TDI. As I said, the VCC on my programmer was not live, so it does require a separate 5 volt supply. We need to wire up the various ground and 5 volt pins for the chip. And then for the 44-pin TQFP, then we need to wire in these pins here. So what I've done is I've done this on a breadboard. And you can see it here, it's already wired up. So I've just got the back of an old business card. And you can see here, this is the JTAG connector. So this is the way how I've made quite a lot of these types of connectors. There's basically some strip board with 4 lots of pins, and then just cut down the middle between the pins there. And so that JTAG connector will allow me to plug in the cable from the programmer here. So this is the USB programmer, and the JTAG cable with the pin there locates in the JTAG connector. There's 2 connectors here. Apparently the TMI one is not supported, so you shouldn't be using that. And then pin 1 is actually going at the top here. And you'll see that I haven't connected up the 5 volts there, and I do actually have my bench power supply connectors here. So just going to plug the bench power supply in there. That basically is our programmer ready to be programmed, but now what we need to do is to look at the software that we need to do this. So some of the information from here came from Peter in the email that he sent to me, and all I'm doing is sort of really just reinterpreting this and providing the information that I'm using. I know Peter mentioned a number of open source tools you could use on Linux and things like that, but I've been using WinCPL, so I'm just going to carry on using that for the moment. So this is more of a Windows-centric along the lines of what I've been using here. The probably most important thing initially is to make sure you're using the right device type for the particular chip that you have, and that's helpfully provided in WinCPL. If you go into the help @MLinfo release notes, then that actually is available there. So if we go into the release notes here, and we can see down the end here, they're all the various devices and what the corresponding device ID is. So the one that we're actually using is the ATF1504 AS in the TQFP 44. Now you'll notice that there's 2 codes here, and the one we actually need is the in-system programming option. So if we choose this other one up here, then we may end up actually writing to the chip, and we might disable the JTAG in-system programming option. And I'll talk about that, how to re-enable that if you do accidentally do this at some point in time, next couple of slides. But you can see here that the F1504 ISP TQFP 44 is the thing that we need. So that's the one we've got there. Now, when I was looking at this, the ATF1504 has 64 registers in it, but there are only 32 registers, or they're generally known as macrocells in the terminology, so MC or macrocell, but only 32 of them are actually connected to pins, and 4 of those pins are also used for the JTAG programming. So if we're using JTAG, we only actually have 28 pins available externally. However, you can still access a lot of the registers using pin node syntax. So this means we can actually use counters and dividers and things like that, and as long as we don't need those pins to be connected to the outside world, it can be used internally. And so I hunted around for this information lots of places, and eventually it was staring me right in front of the face. And if you go to help @MLinfo and then fitter.pdf, then this actually gives us all the information. Now, a fitter is actually the programs provided with the 1500 series, which will allow the software to try and fit your design into the chip in the most efficient way possible. Now, I don't think I'm going to need to use that initially, but if we run out of pins or run out of gates, for example, in the conditions, then the fitter will actually try and adapt your design and allocate the pins and things in the most effective way. So if we have a quick look at that fitter.pdf. Now, the key thing about this is it actually includes quite a lot of background information and some of the configuration options and things, all the various things that you can do to configure this. One thing to be aware of is the 1500 range is different from the 1502 upwards. So the 1500 is discussed separately. Although the macrocells, I believe, are the same, but the way how the macrocells are wired up, and the foldback logic, cascade logic, all those sorts of things is different. Key thing we need to look at is the ATF1504 device definition in various packages. And we can see here, for example, we have the macro cell number down here, and the macro cells go all the way down from 1 to 64. What we'll notice, depending on the packaging that we've got, so we're going to be using the TQFP44 pin here, and you'll see that there is a number of the pins aren't connected. So for example, pin 2, pin 6 and pin 7 are not actually connected, but there are actually these pin node numbers, the 606 and 306, to do with the feedback and foldback. So if we wanted to use the output of a register, we could feed it in using this particular ID. And you can also see that if we were using our 100 pin TQFP, then in fact all of the macro cells actually are assigned a pin. So if we can get our 100 pin one working, that will give us a huge amount of scope for actually replacing an awful lot of logic. Could probably replace most of the video side of the CGA card, for example, with one of these 100 pin PLDs. So finding where the pin node information for this took me a little while to track down, and it's certainly not obvious from the documentation, but this one was just hiding in plain sight. So WinCPL does actually come with the fitter executable files in this folder here, fitters, and the fitter is actually needed to create the ATF1504 series JED files. So these are the JTAG files used for programming the chip. And the fitter can be used to optimize the configuration. So rather than defining pins as numeric, we can define them as names. And then the fitter would assign pin numbers actually to the names. And the output file from this process is a .fit file, which is equivalent to the .doc that we've been looking at previously. Again, this includes a lot of the information about how it's actually achieved the output. Now, there is an extra bit of software that we need. The ATMISP creates a JTAG device chain. Now, the key thing about these in-system programming is that theoretically, if you had multiple chips installed on a PCB, you could use the one JTAG connector to actually program all of them, so you can chain each device together. Now, since we've only got one device, then we only need to worry about a device chain of one, but we need to actually create this chain in the ISP software here, and as part of that, we assign the JED file to it. There's an extra step that we needed before, and then we can then use that to write the JED file to the CPLD using our programmer cable. And the URL here is where you can download a lot of those WinCPL and ATMISP. So let's have a quick look at the data sheet just to familiarise ourselves with some of the issues we need to be aware of. So this is the ATF1504 AS datasheet. So I'm not going to be going through it in great detail. The main things you need to be aware of are the macro cell definition here. So this is a relatively complicated, and I may do a later video to try and explain what all of these different bits are and what all the various terms we need to use in the PLD configuration once I've worked with these a little bit more. I've done an example one here, but I haven't done a huge amount of work with these PLDs yet. And probably the other interesting bit is the pinout information. So in particular, the different lead combinations will have dedicated pins for certain functions. So for example, some of the global clock output enables and things have specific pins assigned to them. The power down pins, or 2 power down pins if enabled, will be dedicated to power down. And as I said, there's 4 pins, I/O pins. If you want to use the in-system programming with JTAG, then you need to have these 4 pins dedicated to that. There are 32 I/O pins by default, but if you're using JTAG, then you only got 28. And you can also see here that we've got 4 ground connections, 4 5-volt connections for this 44 lead TQFP chip that we'll be using. And you can also see here we've got the pin numbers for the JTAG connectors, which we'll be looking at in a minute. Further down here, this table is a little confusing in that we've actually got 2 lots of macro cell information here. We have 1 to 32 down here. So you can see for the TQFP version, you can see where there's a gap where there isn't an external pin, and we have to use the pin node, and then where there is a pin assigned. And then you can see on the other side here, we've actually got the higher ones. And again, you can see here that if we're using our 100 lead TQFP, we've actually got all of the pins are accessible. So these are the two bits of information we need to do the layout for this. So what I've done is I've created a template PLD file. So this is my test ATF1504, and you can see here that I've done with the DIP adapter, I've done the pin layout here. You can see the macro cell numbering is a bit random really, and so getting the pins to make sense on the circuit board and the breadboard will probably require a little bit of work to try and get the pins to come out together. So I've also identified what those JTAG pins are, so I've made sure that I've not assigned those down in this input outputs. Then under the input outputs, everything's organised by macro cell number, and so where we have an external pin, it is assigned to a particular pin number, and where there is only an internal macro cell, then we have the pin node definition here. If you wanted to have the other internal thing, then that begins with a 3 if you needed to use the other one. So hopefully this will mean that when I'm using this, it's not going to be quite so confusing. And we've also got our device here in particular. We've got the ISP TQFP44, which is the device we're using. Now, early in the series, I used one of the gate.PLDs samples, which I modified to run on the ATF22V10. So this was the very simple example. We've got two inputs, A and B, and then we've got outputs, which the inverted A and B, the AND of A and B, the NAND of A and B, the OR, NOR, XOR, and exclusive NOR. With the rules down here, and then the output enable. So what I've done is taken the sample that I included in this other tab here. So we've now got A and B, which are actually macro cell 5 and 4, and then we've got the outputs over here as well. And you can see they're not quite as straightforward to use in this format, but the benefits of having 28 input-output pins, I think, will far outweigh the disadvantages of them being sort of scattered around a little bit. And you can see here that I've used pin 38 as the output enable. This is actually active high, I believe. And also one other point to notice that I'll include in the slide, but should you accidentally disable the JTAG programming, if you apply 12 volts via about a 1 to 2K resistor to pin 38, in this case the OE1, then you can restore JTAG programming, which is the default when the things are shipped. And you can see here we've got the pin A and pin B, and then further on down here we've got the various pins all defined here. Then we've got our logic rules here, and then we've just got the output enables are all set to OE1. So in order to program this, what do we have to do? Well, we need to take our PLD, go into WinCUPL, and because it includes the fitters by default, we shouldn't actually have to do very much. What we now do then is device-dependent compile, and there will be a window in the background there that will indicate that the fitter is actually running. And if we look at the output files, so there should be an updated fit file here, and you can see here that this includes one of the intermediate files, so the initial phases of WinCUPL creates a TT2 file and then goes on to produce the JTAG file, which is the output file. Look at the JED file. So this is the output JED file, and you can see that there is a lot more terms in these JED files than we had in some of the simpler chips. So this fit file includes all of the various options, so things like pin keepers, cascade logic, and things like that. And these are all things which can be changed in properties. Now, I haven't played around with this yet, it's just using the defaults at the moment. But you can see that it tells us that A and B are placed at pin 2 and pin 3, MC4, MC5, etc., etc. And it also includes a little diagram actually of what the chip looks like. Although obviously in our particular case, because we've got it on a DIP adapter, then we've actually got 1 to 22 on the left-hand side and 23 to 44 on the right-hand side. And then the multiplexer assignments, which is where some of the complexity of the chip comes in, program logic, and then there's a pin table here, which is a bit more complex than the simpler chips here. Some summaries at the bottom as well. So the fit file should actually give us a lot of useful information. And for example, I think if we have names within the file which have not got pins assigned, and then that might indicate whether we've got a typo. Now, there are some other files produced as well. So there's the list of the pins. This just produces the pin assignment for the name and the pin number. And I think also information about input and output pins as well. So in order to program this, what we need to do is to fire up our ATMISP software. And before we can do anything, we do need to create a chain file. So I've already got one I've already created. If we did new, we just have to put in the number of devices, so we'll only have one. Then we have to choose which particular type of device we've got. In our particular case, we've got a 1504 AS. And this is a particular instruction. Now we're going to want to have program verify, and then we'd select the JTAG file. So I'm just going to open the one I've already got. So this is my ATF1504 gates. And you can see here that if we edit this, device number 1, we can see that it's initially doing a blank check. And so what we're going to do now is to change this to do program and verify. We don't need to do the secure bit, so program and verify, and then we need to choose the JED file that we've just created. So this is a JED file we've just created. We just need to make sure it's plugged in, and if necessary we can scan for the USB cable. We can see it and find it okay. Okay, so before we program this, we do need to turn on the power to the programmer onto the board, because the programmer doesn't actually provide the 5 volts. I do need to provide the power to this. So if we now click run, and that has in fact verified okay. So if we just have a look at the JTAG log file, so this is the log file produced by the programmer. That seems to have finished this successfully. So now we've programmed our chip. Now we don't need the programmer anymore, but what we do need to do is to be able to test this. Now unfortunately, it's not that easy to test. You can't just plug this into one of the other programmers. So the cheaper programmers such as this one only has 40 pins, so that won't work because we've got 44 pins. But I do have one of these P56 programmers. Now this can do up to 48 pins. So what I've done is I've hooked up these DuPont cables. So there's 2 lots of 24 here. So I could potentially do up to a 48 pin chip. So what I'm going to do is just to plug these in. So the left hand side here, just do the focus on the camera. Move it over a little. You can see this. The left-hand side here is going over here, and the key thing about this programmer is that the chips are actually put in at the bottom here. So I do need to make sure that I put the wires in properly. So I'm just going to wire this in, and I'll show you how we can actually test this. I'm just going to turn the power off whilst we do this wiring in. Okay, so not particularly easy to see that from here, but you can see that is now plugged in. There's a few pins left over at the top of the chip, but that doesn't really matter. So this is plugged into the XG Pro, and although the XG Pro is unable to program this particular chip, the test mode is actually able to test it. So what I'll just show you now is the test mode that I've got for this. So if you run up XG Pro, now you'll see it won't actually have, if we search for this particular chip, you'll find that the ATF1500 series is not in here. So it doesn't know about that. However, the test function here does a logic test, does allow us to create a custom one. And what it allows us to do is when we create a new one, we can actually specify how many pins, and it goes up to 48 pins. So in actual fact, we've got our 44 pins here. I've gone in, I've put in the ground connections here and the voltage connections. Now, I did try powering the chip actually off the programmer here, but it did complain about current protection. So when I'm testing this, I've also got the external power plugged in as well. So I just need to make sure I've got that. And you can see that if we look at the various tests, we've got our A and B inputs are 0 and 0 there, and then we've got the various high, lows, and don't care for the X's there. Then when we've got the 1 and 0, 0 and 1, and 1 and 1. So we can now actually test this. So just turn the power on first of all, otherwise there won't be enough power from the programmer here and it will come up with overcurrent protection. And then the testing has all completed there, and if we just go into one and perhaps change, so pin 44 on this last test. So if we change pin 44 to a low rather than a high, then run the test, and we've got a failure there. So not an ideal way of testing it. Certainly the 100 pin one will be a bit more challenging to test, but it does mean that we can do some sort of sanity testing of this independently of putting it in the circuit. And obviously this is probably where we get the more complicated designs, where using some of the simulation side of things probably makes more sense, in that you could actually check it in a virtual device rather than having to program the physical one. So I'll just change this back. Check this, still working, great. So that means that we've managed to program one of these 44-pin surface mount devices, and that's going to allow me to potentially use this in the CGA video controller. So the 28 pins and 64 macro cells should allow me to simplify quite a bit of the clock logic and some of the video output logic. If I can get the 100-pin version working, then I can probably do virtually half of the circuit actually in this one chip. So one final thing I was just going to cover. So I've covered all the programming. I'll include the URLs and links will be in the description below. So this is re-enable JTAG support. So Microchip shipped the new chips with the JTAG in-system programming enabled. JTAG support does require these 4 I/O pins, so out of the 32 macro cells that you had output on the 44-pin chip, you've only got 28 left. If you were using the 100-pin version, then you would obviously have 60 macro cells left. Now, the official advice is if you have second-hand chips or those where you've disabled JTAG by mistake, the official advice is you have to use a programmer, which I think the ones which I've seen mentioned cost upwards of $500 each, and you need to put the chip in there to reset it. However, apparently, according to this forum post here, if you put the chip in out of circuits, you don't want it connected to anything else, but you put 12 volts on the output enable 1 pin via a 1 to 2K resistor, then this should re-enable JTAG support. So that's a useful one to be aware of should you have this particular problem. So I'm going to break the video there. If I have time, I will try and get the 100-pin version working. The soldering of that is going to be quite a bit more fiddly, but I will do a follow-on video to this as and when I do get that working. So thanks for watching. If you want to see the rest of the Breadboard PC version 2 series, then there will be a link in the description below and in the playlist at the end. And there is a playlist for the PLD mini-series as well that you should be able to go through all the PLD videos should you want to. So thanks for watching. If you don't want to miss out on future videos, please hit subscribe. And if you found the content interesting and useful, please hit like. It just helps to make the videos available to more people.